All right, so problem 66 is a power problem. We got 6 dogs pulling a dog sled. So we have these dogs all connected together, and then we have our sled back here with people on it. And they're all connected together, just like the Iditarod race. We want to know the maximum power output during the acceleration phase. Okay, so several things we have to get here. Remember, power is going to be work over time. So we have to figure out how much work the dogs are doing. And we got to figure out how long they do it while they're accelerating to figure out the amount of power coming out of it. So the first thing we got to do is remember work is equal to force times the distance times the cosine of the angle. So we need to know the force. So to figure out the force, we're going to do a free body diagram. The dogs are applying a force, we're going to call it F. We do have friction we have to worry about, which is the kinetic friction this way. We have a normal force and we have gravity. This is the free body diagram of the sled. We don't really care about the y direction except to deal with friction. So the net force is going to be the force applied by the dogs minus the friction force. But remember, it's accelerating, so we have to replace this with ma. So ma is equal to the force minus the friction force. Or ma is equal to the force minus mu sub k times the normal force. Well, in this case, the normal force, we do with F net y, just n minus mg. This is 0, so the normal force is equal to mg. Okay, so what we want to do is find the force the dogs are applying. So I'm going to solve this for F. So F is going to be equal to ma plus mu sub k times mg. And that'll give me the force. And so the mass is, the sled's mass is 220 kilograms, so this becomes 220 times 0.75 plus 0.080 times 220 times 9.8. And we get that the force to accelerate that is 337 newtons. So to accelerate the sled, you had to get a force of 337 newtons. But they didn't ask that. They still asked for the maximum power output. All right, so we got the force, which is going to go in here. We have to figure out how long or how far they go during this time when they accelerate to plug in for the work. And then we got to figure out how long it is. Okay, but we're only given that they start from rest and that it accelerates here until it reaches a cruising speed of 12 kilometers per hour. So what we have to do is figure out what 12 kilometers per hour is in meters per second. So we have 12 kilometers over hour. Remember, there are 1,000 meters in a kilometer, and in an hour there's 3,600 seconds. So we get that this is equal to 3.33 meters per second. So that's the speed, the final speed. So to figure out what the distance is, we're going to use our constant acceleration. Remember this equation, plus 2a x minus x naught. All right, x naught is equal to 0. The initial velocity is equal to 0. So we can say that v squared is equal to just 2ax, or x is equal to v squared over 2a. Or in this case, it's going to be 3.33 squared over 2 times 0.75. And you get that x is equal to 7.4 meters. So that is the distance that's going to go into here for D. But we still have to know the time. So we figured out how far it goes while they're accelerating, but we need to figure out how long it takes. And so the easiest way to do that is use our other constant acceleration equation, because we know that the initial velocity is 0, the final is 3.33, and we know the acceleration is 0.75 times t, and so you get t is just equal to 3.33 divided by 0.75, or t is equal to 4.44 seconds. All right, now we got all our variables we need to figure out the power. So the power is going to be work, but work is equal to FD cosine, but the angle is going to be 0 because the force is in the direction of the motion. So that just becomes 1 over the time. So this is going to be equal to 337 times 7.4 all over 4.44. And the amount of power they put out is equal to 560 watts during the acceleration phase. So this is the answer here to part A. Now to part B, we want the power output during the cruising phase. Well, this is actually easier because we can use that the power is just equal to FV cosine the angle. But in this case, the force and the velocity are in the same direction. We know the velocity already, so the power is just going to be equal to 300. Oh, I'm sorry, hold on, we can't do this. Things change here, right? I made a mistake. The force is not the same. This is the force while they're accelerating, but when they're going at cruising speed, there's no acceleration. So now our F, if we redo our free body diagram, exactly equals the kinetic friction force. So we have to do F net x is equal to F minus the friction force. Or the force they apply is equal to the friction force. So the force is equal to mu sub k times mg. Or the force is equal to 0.080 times 220 times 9.8. And you get the force is equal to 172.48 newtons. That's the force that I have to plug back in here. So power is equal to 172.48 times the velocity, which is 4.44. Cosine of 0 is 1, so the power is equal to I'm sorry, hold on. This is not 4.44. Sorry. This is the velocity. And you see the velocity up here. I plugged in the wrong number. This is 3.33. Okay, I plugged in the time. I don't know what I was thinking. So this is the force. This is the velocity. So it's 172.48 times 3.33. And you get the power is equal to 570 watts. So, to summarize, while the dogs are accelerating the sled, they have to apply 560 watts of power. And while they're cruising, they're applying 570 watts. And that is how you do that problem.